Okay, we continue convolution and we will discuss it in the continuous time case. So we had seen how it was developed in the discrete time case, and in the continuous time case it is essentially a similar kind of development. We start by looking at the approximation to the continuous time impulse function, which we had seen earlier, which we call it now as delta delta of t, which is a short pulse of width delta and amplitude 1 over delta. Okay, this we call it as delta delta of t, and it is defined as we just said, 1 over delta between 0 less than t less than delta, otherwise it is 0. So so you note that delta multiplied by delta delta has unit amplitude, correct? So the development of the continuous time convolution stems from being able to approximate a continuous time function x of t as an approximation using these shifted delta functions, these delta delta functions, that is short pulses of width delta. So here you can see how it is done. So this is a continuous time x of t, and we are representing x of t with various scaled and shifted versions of our delta delta of t. Okay, this is the t-axis. So this is the first pulse is from 0 to delta, second is from delta to 2 delta, and so on. So this is some arbitrary k delta, where here 1, 2, 3, k and so on are integer values. So now in the approximation to x of t, we call x hat of t, can be written as a linear combination of these scaled and shifted delta functions, delta delta functions, multiplied by the delta, of course, to make it unity. So essentially the weights of the linear combination here is equal to the x of k delta, which is essentially the value of the function x of t at the time k delta. So we use this expression to represent an approximation to x of t, which we term x hat of t. Again, this is very similar to how we developed it in the discrete time case. So the point here is that as the width of the pulse becomes narrower and narrower and narrower, in the limit our approximation x hat of t becomes equal to x of t. When you apply a limit where delta tends to 0, the width of the pulse essentially is becoming as narrow as possible, and hence this approximation here, which we saw earlier, is going to be equal to x of t, which is the underlying function which we are trying to approximate. So essentially what will happen is this summation here will be an integral, and we write it as x of t is equal to minus infinity to infinity x of tau del of t minus tau d tau. Okay, so we are basically writing the given function x of t, which we want to approximate, as a integral combination of scaled and shifted delta functions. We have seen this earlier. This is nothing but the shifting property of the delta function. So essentially one more view is like this. This is, now we consider the tau axis, we see them all as functions of tau. So now we have the function x of tau, which we want to approximate, and we have a shifted delta function at time equal to t. Okay, the area under the delta function is 1. This is delta of del of t minus tau. So essentially now when you take the product x of t multiplied by del of t minus t, essentially what you will get is a scaled delta function of amplitude x of t. So the area under this delta function is equal to the value of x of t and the location of the impulse. We have seen this result earlier, correct? So coming back to this equation, this equation is nothing but we are expressing x of t as a scaled and shifted combination of delta functions. So now to develop the response of a linear system, we will first assume this one first. Just see this. Now this is our delta delta of t, which we just saw earlier, right? Delta delta of t. Now suppose you give delta delta of t minus k delta as input to the system. So essentially this is nothing but this. This is over t. This is a function of t, and this impulse is located at k delta. So this is delta delta of t minus k delta. The width of this pulse is delta. Okay. So if you give this as input to the system, let us assume that the output is h hat of k delta of t. Okay. So this is the format in which we expect the input and the output. For this input, we are getting h hat k delta of t. So this we are assuming a linear system here. So essentially now, if you want to develop the output for some arbitrary input, again by using the property of linearity and applying the superposition property, essentially what we will do is now the output y of t, we will approximate it as y hat of t, where y hat of t is nothing but the scaled outputs, because we are applying the linearity property here, because the system is assumed to be linear, and this shifted delta delta is giving me h hat of k delta of t. A linear combination of such delta deltas will give me an approximation y hat of t, where the weights of the linear combination are given by x of k delta. Okay. And as we saw earlier, when the pulse width is very small, as in the limit when the delta, the capital delta, that is basically the width of the pulse, tends to 0, our approximation y hat of t becomes equal to y of t, and this expression is remaining the same, what we just saw earlier. And essentially this will become an integral x of tau h tau of t dt. So this is my y of t. Is now becoming this expression h tau of t dt. Okay. So this basically represents the response to a delta function, to this double delta function located at t. Yeah, h tau of t is the response to del of t minus tau. Okay. So remember, we are seeing these as functions of tau. So this is the delta function located at t. So from the previous argument, when any x of t can be represented as x of tau del of t minus tau d tau, integral of this. So we saw that any given x of t can be represented as a scaled and shifted integral of delta functions. The output will now become y of t. Y of t becomes minus infinity to infinity x of tau h of tau of t d tau. Okay, so this is exactly the parallel build-up of the discrete time case. We are just representing a given input as a linear combination, or this is a continuous sum of delta functions, scaled and shifted delta functions, and because of the linearity property here, because the system is assumed to be linear, the output is going to be a scaled and shifted is going to be a scaled versions of the outputs produced by each of those shifted delta functions. And similar to what we did in the discrete time case, if the system is also time invariant, then we have h tau of t is equal to h0 of t, h0 of t minus tau. Okay, so essentially if we give del of t as input, we assume we get h0 of t as output, and so if we give del of t minus tau as input, we get h0 of t minus tau as output. So essentially this will lead us to the convolution integral for the continuous time case, where the output y of t for a arbitrary input x of t is equal to x of tau h of t minus tau d tau, and we represent it as x of t convolved with h of t. So we have the same notation here, and this operator is now continuous convolution for continuous time. Okay, so the development is pretty much similar and very parallel to the discrete time case. We have rushed through some details here. You can always refer to the textbook, but essentially again we are the basic idea is that we are representing a given signal as a linear combination of, or as a integral combination of scaled and shifted delta function. This is from this that we end up with the discrete time, with the continuous time convolution. Now pretty much similar to the continuous time case, we will just look to the discrete time case. We will look at we will quickly look at a problem. This is an example which is there in the textbook. This is example 2.6 from Oppenheim's textbook. So given my x of t is given as e raised to minus at ut, which is essentially this, which is an impulse which is basically a decaying exponential signal starting at 0 because of u of t. It decays here, and my h of t is given as u of t. Okay, so this is my x of t, this is my input, and this is the impulse response of the system h of t. So now if you convolve this with this, what is the output? You are asked to find out what is the output. Okay, so similar to how we did convolution in the discrete time case, the same logic applies here as well. So we are given now h of t. We now write it, we now flip it just like how we did it in the discrete time case, h of t, and now we shift it as h of t minus tau. Okay, here again now we are seeing this is my h of t, but here now we are seeing this as a function of tau. Remember, we are seeing this as a function of tau. So this is h of t minus tau, which is a flipped and shifted version of h of tau. So if t is less than 0, my h of t minus tau looks like this, and if t is greater than 0, my h of t minus tau looks like this. Okay, so now if you see it all together, now if you see it's all together, this is my 0, all over here is 0. So this is my x of t. So when the value of t is less than 0, we see that h of t minus tau and x of tau do not overlap. So essentially if you multiply, you will get 0. So essentially the output y of t is going to be 0 when t is less than 0. When t is greater than 0, we see that the shifted the flipped and shifted h of t minus tau looks like this. So you can see now if you multiply x of t with this h of t minus tau, we see that this is because the value of this is 1, because this is a flipped unit step, correct? This is a flipped unit step. So when you multiply, you will see that for a given value of t, the output will be the sum or the area under the curve from 0 to up to the value of t. Wherever is the value of t, this area is what will become my y of t. So essentially my y of t essentially becomes integral 0 to t e of minus a tau d tau. Okay, this is just by applying the convolution integral, and you can solve this, and finally you will get the answer y of t as 1 by a 1 minus e raised to minus at ut. So this is the output which we will get for these two inputs. Okay, and the output basically looks like this. Okay, so it is a positive output because the output for t less than 0 is going to be 0. So this is a solved problem from the book. There are various other examples in the book. Please go through them and please try to solve them.